Hey guys, welcome to the third video of Codeforce Machine Learning. In this video, we are going to continue looking at the design aspects. So let us first take a look at the support folders that we have in some of the library projects. Now the support folders are present in some of the algorithm libraries. They will not exist in some of them, but they will exist in where data structures are needed, like decision trees and neural networks. So in this case, for decision tree, the support folder contains basic classes that are used by both the model and the build. Like these are common classes which can be used anywhere in any of the build classes or the model classes. So for example, this is a decision tree node. Now, if you're familiar with decision trees, a node is a very fundamental building block, and it's likely used to whatever algorithm you use, whether it's ID3, CART, or C45. So here we have a decision tree node which is built as its independent class, and then we instantiate this class to create like each individual node inside the decision tree. So this way we can reuse this class everywhere, and when we are building the tree, it's going to be composed of multiple of these classes. So primarily it contains the data structures to store the value and some information about its parent. So it's kind of like a linked list, but it also has some built-in functions like add child, get the child with value, and attribute value. This is something to support the decision tree operations. Similarly, we have some in neural networks. Now, neural networks are a little bit more complicated than decision trees. So here we define a single class to define each layer. So we have a layer class, which is again in the support function. So this is encapsulating a single layer that is part of the neural network. And if you're familiar with neural networks, each layer can have multiple functions in it. So these functions are basically also called as nodes or neurons that are inside. So this layer can have more than one neuron depending on how we have configured the neural network. So this way, this offers a nice encapsulation of all layer operations. Now for the input layer of a neural network, we need a slightly different class because it has some other functionality that are not common in your intermediate layers. So here the single layer input actually inherits from a single layer class, and then it overrides some basic functions like get value, and has another function called set data, which basically takes your input and sets up your input layers. Now when you're building the neural network, all these layers are interconnected, but that is actually taken care in the build when you're building the neural network. And once the model is built, this model class will also compose of multiple single layers and a single input layer. Now in neural networks, we also have activation functions. And activation functions are very important because they govern how your neural network is going to behave, and also determine the accuracy of your neural network, whether you are using it for regression or for classification. So we offer multiple activation functions here, but the main thing is you can add your own activation function. So what we have done here in the DASPIC library is created an activation function interface, which essentially implements two functions, get value and get derivative value. And if you're familiar with interfaces and object-oriented programming, this is a contract that any class that implements this interface has to have these two functions. So for example, let's take a look at the sigmoid activation function, which is a very common activation function. So here the sigmoid function inherits from the activation function interface, or we can also say it implements the activation function interface, and it has the get value and the get derivative value. Now we have the get derivative value, it is the dy by dx, and this is very important when you are implementing your neural network. So sigmoid is a very common activation function used. Now let's take a look at the linear. So linear, essentially the rate of change or the derivative is simply 1, and we implement the get value here. So this makes it easy that we can replace any activation function in any of our models just by creating a concrete class. Like in this case it's a linear class and we inherit it from the eye activation function. Inside the build classes and the model classes we only refer to eye activation function. So when you're building the neural network or consuming a model, the model has no knowledge of what is the kind of activation function. It just simply calls the get value and the get derivative function because it references the interface, and then in your concrete classes you can give more information or actually implement the get value and the get derivative value. So this way, this design pattern of support allows you to give some additional functionality that is common only in the specific algorithm that you're implementing. Like this support functions for activation functions, single layers and single layer inputs are only useful in neural networks. They're not going to be used in deep learning. If they are like useful in other areas across all the algorithms, then we won't have them in the support function inside the algorithm. We'll have it in a more common area where it is accessible by other functions. All right, now let's take a look at a unit test. We haven't covered unit tests much. So at a high level, I've shown the unit tests have the same folder structure as your code base. So if I minimize the code base, I have the algorithm, common, and the math classes. Similar structure exists in unit tests. Now unit tests also have a common core. It's called the unit test based, and every other unit test that we implement actually inherits from this function. So we have built up a design pattern also in the unit test to control our complexity. Otherwise, things are going to get quite complex. So what this common function of this common class here, the unit test base, it provides a set of data structures or the data that we can use in testing other algorithms or other common functionality. So for example, we have a get dataset file name. So in this case, we have created multiple CSV files that include some data that we are going to analyze. So remember that when you're building a machine learning library, it's a mathematical, I mean, essentially it's mathematical functions. And whenever you are implementing mathematical functions, unit tests are very, very important because you have to test all the cases and make sure it's giving the correct results. In fact, mathematical functions are very well suited for unit tests because you know the set of inputs and you know exactly what output it gets. So the same thing we have done here, that we have provided iris dataset, a Pythagoras dataset, and then we know that whatever algorithm we have applied, like if you're doing a regression in this Dasmic library, we have given a lot of data sets for Pythagoras theorem and build a model that essentially emulates the Pythagoras theorem and have a separate blog article on it. So this data set, we know what the actual result will be. So whenever we are building a neural net or using like regression algorithms, linear regression algorithms or polynomial regression algorithms, we can feed in the same data set and we know that the output is going to be within a certain range. So this get dataset file name will be used in a unit test for both neural networks, for regression, and can also be used for classification problems. So we like have a function to get the dataset file name, then we load the actual dataset from this. And when you load the data set, it actually stores in an internal data structure, and then you can get a single training data set for test. So this is like all common functionalities that you are going to be using in your unit test. So for example, let's take a look at the neural network algorithm here. So we are looking at back propagation, and as you can see, it inherits from a base test. Now the base test is another base class that is defined only for the neural network, and as you can see, the base test inherits from the unit test base. So This allows us, in the case of neural network, because testing for neural network can get quite complicated, so we have created a separate base class and then inherited from the unit test base. Now we can also define some specific data set that we only want to use it for the neural net testing, but we also have the option of using the data set that is provided in the base class. So as you can see, for neural networks, we have defined some other data. Now we can also move this into the base class, so that just to make this training set available to other algorithm testing. So that is something that can be done. But right now we only have it only for in the neural network unit test library. So here's an example, right? Load from dataset. So we are loading a Pythagoras dataset, and this is actually defined. If you go to definition or go to implementation, this is defined in your unit test base class, which is composed on unit test code. So this also gives us a design pattern that as we are improving our unit test or expanding on our unit test, we can decide to have it at a common level because all the wiring has already been done. So if you add it at a common level, it will be accessible to all the other unit tests. Or you can add it at a local level for each algorithm. So with that, we have capped our review of a design. So from the next video, we will start taking a look at some of the algorithms, starting with the mathematical routines, because mathematics is the foundation of all machine learning. Till then, see ya.